So if this circle is rotating by theta degree, then we calculate these are the length of this arc. By definition, this arc is theta r, right? So because assuming that there is a rope hanging the mass here, when this circle, when this pulley rotates by theta angle, so it actually pulls this much rope upward. So which means your x is the length of the arc. Then we can use this relationship to replace all the x in the equation. So first of all, yes, x is theta r. Your x1 is also theta r because it's on the same circle. Your x2 would be theta times 2r because it's on the larger circle there. And then x3 would be theta times 2r as well. So then we can replace all the x by theta. Your t becomes half m r squared theta dot square plus a half j theta dot square. And then your u is half k theta square r square plus half k theta square 4r square. And then we can sum them together. It's 2.5 kr square theta square. So let me erase this. So the next one is q. Q is half c, x3 is here, so we have times 4 theta square r square. And because it's velocities, then we have to add a time derivative to these theta. If you don't know where I got these theta dots, we can focus on this relationship and calculate time derivatives on both sides. So you have x3 dot equal to theta dot times the constant 2r. And then we can simplify it. It becomes 2cr squared theta dot square. Okay, so up to this point, we have T, U, and Q. They're all in terms of theta. So the next step would be calculating, partial L, partial theta dot. So if we check the class notes, your L is T minus U. And then we know that only the T term has theta dot in it. So it becomes mr squared theta dot plus j theta dot. And then again, we need to calculate the time derivative of this term. So it's really easy. Just change the single dot to double dot. So the second term we need to calculate is partial L, partial theta. So in this case, we only focus on the U, the potential energy. So it's simply 5 kr squared theta is from this term. And then our equation on the left-hand side would be, I think I'm running out of space. Let me write it on top. So it would be mr squared plus j theta double dot. So that's from the first derivative plus, oh, I think here we need to add a minus side because you have a minus here. So that's something we need to pay attention. So the sign is the place you usually make mistake. So just to pay attention. So the reason why I noticed this mistake is because without this negative sign, I might have negative coefficient in front of the theta term. In that case, your system becomes unstable. But from these physical system, we can easily tell it should be a stable system. So that's another way to quickly identify an error in your solution. So we have 5k r squared theta. So on the right hand side, you should have minus partial q partial theta dot. So that's gonna give you minus 4cr squared theta dot. So these terms should be placed on the right hand side of the equation. So it becomes 4cr squared theta dot. So eventually that's going to be our equation of motion. So this case is very special. We never use that small rotation relationship because the wire is rotating around the circle here. So we directly have the arc length equals to the deformation. And then, so after this online meeting, what you can do is you can try to include the influence gravity in your solution, and then to check what that gravity was. So what kind of difference does the gravity make to the solution? So that's actually the last question from last year's exam 1. So that should be the most difficult question you should expect in this exam. So do you have any questions? Okay, so Q, if you want to know more about Q, then if you have your lecture notes by your side, then what you can do is open the lecture notes for the 3rd lecture, and then on page 4, you should be able to find the definition for Q. I think I misused the late symbol. So the Q here should be the R in the lecture notes. So I think that's the reason why you have the confusion. So, okay, so I think I'm, okay, so cool. So I think I can move on to the next question. Let me see, do it. Oops. What happened? How can I? Clear. Oh, great. All right. So the next question is actually a simple undamped system. So we're given the system coefficients M and K, and also give the initial conditions. We need to find the solution in time domain. So whenever you see an undamped system, that's from lecture number 2. So that's why you have to take out your lecture 2 notes. And then is actually an example on page 2. So we know that if it's an undamped system, so the time domain solution should be a sine wave. So again, in order to define a sine wave, we need to find the amplitude, frequency, and phase lag. Okay, so frequency is easy in this case, because it's undamped. So it's directly square root of k over m. That's gonna give you, let's see, 2 radian per second. And then both the phase lag and amplitude that depend on the initial condition. So what you need to do is recall those equations, or you can just search your notes. So the amplitude A is square of initial position, initial velocity over natural frequency. But then one thing you have to pay attention here is the unit. So here, the initial position is given by 1 millimeter. But then in order to keep your units consistent, you have to I think the best idea is convert it into meter. It's going to be 0.001 meter. So this case is special. You can still leave this millimeter unit there because your velocity is 0. But then if in the if in the exam the velocity is not 0, if I give a velocity like 1 meters per second, then these two units are not consistent, you might have an error. Okay, so let's calculate these. We know V naught is 0, so it's super easy. So initial position is X naught, so it's directly 0.001 meter. And then the phase lag, if you go to your notes on page 2, that should be invert tangent omega n X naught over V naught. Okay, so that's something special here. So you have invert tangent. So what's inside this bracket is actually infinite, and it's positive infinite. So the reason why we get this positive infinite is because if you look into all these three variables, omega n, we already know that is 2. And then X naught, we already know that is 0.001. So both on the numerator, you have a positive value. So in the denominator, you have 0. A positive value divided by 0, that should give you positive infinite. And then if you recall the shape of your tangent function, that's like a tangent function. That's your phi. That's tangent 5. So if your tangent 5 is infinite somewhere in here, then your phi value should be half pi. So that means this should give you half pi. If you have a calculator or MATLAB, you should that can help you to calculate this number. But if without those calculators, you can just find this half pi from the function plot. So we know phi, we know A, we know initial condition, then we know the plot. So it's super easy because we just need to follow the equation. But what I would like to suggest is in this question, what we're doing is I'm giving you the parameters and then you draw the plot. So there is another homework question, I believe is homework. So there is another homework, which is homework 4 in lecture 2. So in homework 4, we're actually doing the opposite. I'm providing you the plot and then ask you to derive these system parameters. So in the exams, you should be able to do both. So either from function to plot or from plot to function. Okay, any questions about this homework? All right, I think I can move on. Oops. The third one is about these L-play landing system. I actually got a lot of students coming to my office, ask about this question. So again, we need to use, in this case, it's better to use Lagrange's method to derive the equation of motion. So first of all, we have, I always would like to start with kinetic energy because that's the easy one. So we have an aircraft wheel, which has a rotation in it. That's half J theta dot square. But then that's only part of the kinetic energy. this wheel is rotating at the same time, it's moving up and down. Because of that linear motion, we have to consider an additional, we have to add an additional term for the kinetic energy. So once you have this T, the U is simple because it's only the spring moving down by X. So that's half kx squared. And then because we have damping in it, we have to use the Rayleigh dissipation function. Here I'm using the corrector symbol, R. So that's half C x dot squared. And in this case, the X and theta, the relationship is already given, so we don't have to worry about it. So that's X can be replaced by theta R. So your kinetic energy is half J theta dot square plus half M R square theta dot square. Your U is half K R square theta square. Your R is half C theta dot square R square. Okay, let's recall the Lagrange's method. We have L equals to T minus U. And then we want to calculate, so the final equation of motion is partial L, partial theta dot D, and then calculate the time derivative minus partial L, partial theta equals to minus partial R, partial theta dot. Then you just need to calculate the time derivative or the derivatives for each term, for each part. So I think there is a better way to do it because we already know that the first derivative is the function L with respect to velocity. And then we look into this energy, kinetic energy and potential energy. So the only energy that is related to velocity is the kinetic energy, right? So that means your partial L, partial theta dot should equal to partial T, partial theta. And then the second one is partial L with respect to position, L function with respect to position. So only the potential energy is related to position. So we can simplify it to minus partial U, partial theta. So by doing so, we actually have a simplified version of Lagrange's method. So that's partial T, partial theta dot D dt plus partial U, partial theta equals to minus phi partial R, partial theta dot. You may use this function in this vibration class because we're only dealing with linear systems and all the components we're dealing are springs, dashpots, mass. So they're all linear components. So that's why this relationship always stands. But then if you go outside of this classroom, you might need to deal with nonlinear systems. Then these two relationships might not stand anymore. So these two, number one, number two, because your potential energy might also depend on velocity. So in that case, you need to go back to the original form. I'm providing these one specifically for this class, for all these highly linear systems. The benefits for this new equation is actually, so you can avoid you can have less calculation error because then you don't have to write your L out. You just directly calculate part of the derivatives with respect for these T and U terms. Let's check if that's correct. So the first one is partial T, partial velocity. So it becomes J theta dot plus mr squared theta dot. And then we calculate time derivative. It becomes doubled up. So that's your first term here. And then the second term is for the potential energy. We have kr squared theta. That's the second term here. And then we know that it equals to minus partial r partial theta dot is minus cr squared theta dot. If you want, you can move the right-hand side to the left, and then it becomes, oops, j theta double dot plus mr squared plus cr squared theta dot plus kr equal to 0. So that's your equation of motion. Because we know that this system should be stable, so all the coefficients are positive, so that makes sense. And then the other way to check it is if you look at J and mr squared, so mass times distance square, that's going to give you the unit of moment of inertia. So your mr squared has the same unit of J, so that means, so you don't see any like unit inconsistency there. And cr squared, kr squared. So then if you check your unit of your coefficients, they should be the same. And then the next step is, I'm giving you all these parameters. You need to tell me the damping ratio and damped natural frequency. So what you can do is you just replace the J, mr squared, cr squared, kr squared by these numbers, and then go to your lecture number 3 notes, and then find out the natural frequency. So I think I'm going to skip these calculations there. It's just simple calculation. So any questions for these for the third question? So, all right, I think I can move on. So I want to emphasize this question a little bit. So when you use these simplified formats, that's only for linear systems. For more complicated systems, you have to go back to the original shape. All right. Oops. So the fourth one is system simplification. I can guarantee you that you're going to see one of these questions in your exam. So you're going to see a lot of springs connected to a mass, and then you need to simplify this system into something like this. Basically, you need to find the equivalent values for this system. That's 10 kilogram. And then you have K effective, and then C effective. So when you have a lot of springs connected to a single mass, you can always combine these springs together, and then eventually you can use one spring coefficient to represent all the springs. We call this effective spring, and then we need to find the effective spring constant. So the difficult part is, so the last time when we learned about spring groups, that's in lecture 4. So if you go to slide 5 in your lecture 4, we actually discussed the 2 types of spring groups. The first type is series. When you have 2 springs in series, then the final one that's the relationship for your K effective. If you have 2 in parallel, then your K effective is the sum of these two springs. Okay, so as I said, the way I remember it is when you have a lot of springs connected in parallel, you actually have a steeper system. So that's why you should have a summation. When you have a lot of springs connected in series, you should expect like a smaller stiffness. So that's why everything is inverted. Okay, so let's first look at these. Let me see. So let's first look at the springs on the right. So these two, they're definitely in parallel, right? So we just sum these two values together. It becomes 11. And then the other thing is these 2 kilonewton per meter and 3 kilonewton per meter springs, they're connected in series. Then following these relationship, we have 1 over x equals to 1 over 2 plus 1 over 3. And then we know that x is 566. Right? That means we can use a single spring to represent this. And then the stiffness of the single spring is 5 over 6 kilonewton per meter. And then this one, the new spring here and the bottom one is, they're in parallel. So you can merge them. So you have on the right hand side, you have 4 plus these. That's like you have 11 here, and then you have your damping dashpot. So we name these as K1, these as K2. So my question is, what's the relationship between K1 and K2? Are they in parallel or are they in series? Okay, I got one answer. Any other different opinions? All right. So, okay, they should be in parallel. So it doesn't really matter. So it might look like these two are connected at the same point. It looks like they're in series, but they're actually in parallel. What you can usually do is you can move things around. So what I usually do is I want to merge the ground part because these are two at the same ground. What you can do is you can erase one of the ground here. Oops. Come on. And then you connect these spring to the same ground. And then the other side of these spring is connected on the mass. So that means you can connect to the other side of the mass. So it becomes a parallel spring group again. So eventually you will have K effective equals to K1 plus K2. That's 15, 5, 6 kilonewton per meter. So when you see a lot of springs, so don't panic. Just simplify, just eliminate them one by one. If you recall my method, I first erase this spring, then I merge these two springs, and then erase this spring, and then eventually merge the last two springs. So by doing so, we got the K effective. So the mass is still the same. The C effective is always is also the same because we don't have more than one dashpot there. So we know the C, we know the K, we know the mass. So we need to determine what if the system is overdamped, underdamped, or critically damped. So in order to judge what type of system we have, so we need to calculate the damping ratio. if you recall, your damping ratio is C over 2 mk. Right? So your C here is 1 kilogram per second. You have 1, you have 2, your mass is 10 kilogram. And then what is the K? The K is 15, 5 over 6. You have to pay attention to the unit. It's kilonewton per meter, so you have to times 1,000. So let me see what's the value here. If you calculate it out, it should be 0.0012, definitely smaller than 1. So it is underdamped. So, right. So any questions related to this homework? All right, I think I can move on. So if you don't have time to write down all the solution, I'm going to post the solution on Blackboard because I thought I can save the solution, but apparently I cannot because when I swap it, I have to delete the solution. All right, cool. Okay, so that's the last question we are going to discuss today. And so in this case, we have the displacement plot. And then we need to determine the damping ratio of the system. So we learned these in lecture 4. If you go to page 6 or slide 6, in lecture number 4, we actually derived the way to find the damping ratio. So what we do is, when you see a plot like these, the first thing you can do is you need to recall the time-dependent solution. Sine omega d t plus phi. So we know that this is actually a sinusoid wave whose amplitude is decaying exponentially. And then the frequency of that sinusoidal wave is actually omega d. That's something you need to remember. So the frequency is omega d, is not omega n. That's different from the very first question we're dealing with. So in the undamped systems, when a system have no damping, so the vibration frequency is always omega n, the natural frequency. But then here, because we have damping, so the system is vibrating at a different frequency. So how to find the frequency? We already know that frequency is related to period. So from here, we can easily find the period. So let's find a complete sine wave, starting from 0, going up, going down, going back to 0. So at here, that's 1 period. So we know that your t is 4 seconds. And then you have omega d equals to t over, sorry, that should be the opposite. It should be 2 pi over t. We can plug these number 4 seconds back into these and becomes half pi radian per second. But then the problem, so the question asks us to determine the natural frequency, which is omega n, and then the damping ratio, which is zeta. The last one we already did, that's omega d. Omega d is half pi. But we already know that omega d is a function of omega n, and damping ratio zeta equals to half pi. That's one equation, but we have two unknowns. We need to find another equation. So let's recall the lecture notes. We already know that the damping ratio is theta. Sorry, let me use a different one because my writings for theta is really confusing. I'll change it to sigma. 4 pi squared sigma square. Oops. So if you recall, these delta is actually 1 over m minus 1 log x1 over xn. So n means the nth peak. X1 is the value of the first peak. Xn is the value of the nth peak. So in this case, let's find all the peaks in the system. So the first peak is here. The second peak is somewhere in here. So we know that your x1 is 0.75. Your x2 is, let's see, that's 2 point, we have 1, 2, 3, 4, 5 steps. So each increment is 0.05. And then we have 1, 2, 3, 4, that's 0.2. But then it's slightly higher than 0.2. We just estimate it as 0.21 perhaps. So if you see a chart like these in your exam, just make a best guess. So it doesn't have to be exact. Any values that make sense will be okay. So let's use 0.21. And then we know that because that's two consecutive peaks. So your n equals to 2. Let's plug all these back into the data function. It's 1 over 2 minus 1 log 0.75, 0.21. If you want to calculate, your delta should be 1.27. So we know the data, then we can plug this data back into this equation to get our damping ratio. Your damping ratio should be 0.1986, smaller than 0, smaller than 1. So your system is underdamped. So that makes sense, right? So only for the underdamped system, you're going to see oscillation. If you get a zeta greater than 1, then you can never see such a plot. That's actually one way to check your solution. If for a oscillating damped system, you're actually getting a zeta greater than 1, then you should think about it twice. And also, your zeta cannot be negative. Your damping ratio cannot be negative. Okay, once you have zeta, you know omega d, then you can easily calculate your omega n. Your omega n is omega d divided by 1 over zeta, 1 minus zeta squared. That's 1.6027. Because for underdamped system, your zeta is so small, so your omega n should be very close to omega d, usually slightly higher, but this should be really close. All right. So that's it. Well, that's a good question. So yes, you can definitely use. That's not the only way to find the damping ratio here. So the other way to find damping ratio is you can also pick the third peak, and then you can from x1 x2 you get one damping ratio value. From x1 x3 you get a second damping ratio value, and then you can do average. So in practice, that's actually what we usually do. You can code it up in MATLAB, automatically find those peaks, and then do a moving average to find the actual damping ratio. And the other thing you can do is, instead of you picking peaks, you can also choose the valley. That can be a y1, y2. As I discussed in class, these two values should give you the same result, or I mean, similar results. So there were no unique ways to do it. So pick whatever you want. And eventually, I'm expecting more than one solution for this type of question. And also, yes, you can always use these methods for to find the damping ratio for underdamped system. Yep. But if you have MATLAB, actually there are better ways to do it. So you can do, because you already know the function, you can actually use MATLAB to do a curve fitting. You provide this function to MATLAB, and then MATLAB is going to search for different zeta, trying to best fit this curve. That's another way to find, that's the other way to find damping ratio if you have numerical methods. And also, during the exam, I would recommend you to pick the first two picks, because the other thing is you have to think about is the signal to noise ratio. So if you have a data like these in practice, the smaller the peak is, the more noise it has in the signal. So that means the third peak is actually less reliable than the second one. Okay. So let me see. So if you want, you can go to check the signal to noise ratio. If your signal itself is too small, then signal to your noise level is the same, then signal to noise level will be reduced. So that means your X3 is less reliable. If you do want to use moving average to average out the damping ratios, then you might want to consider putting less weight for X3. So you will say, okay, the first point is like 80%, and then you only consider the second damping ratio as perhaps 20%, and then keep reducing. All right, so any other questions?